We're still talking about functions here in section 2.6, and specifically we're talking about transformations of graphs. When we talk about transformations of graphs, we're talking about graphs doing things that their parent functions wouldn't normally do. And for us to know what their parent functions would normally do, we need to know what the general parent functions are. In this class, there are several parent functions that we're going to focus on, and that's the first thing that we look at here in this unit. So linear functions. We've talked a lot about linear functions already. That's lines, graphing linear functions, right? The parent function for a linear function would just be y equals x. That function looks like this. It starts at 0, 0. It goes up 1 over 1, right? Because the slope is 1. Y equals mx plus b is the same thing as 1x plus 0 if we wanted to look at it that way. Y equals x. And then any translation or shift or shrink or anything like that, we're doing to this parent function, y equals x. Another parent function is the quadratic function. That's y equals x squared is the parent function, right? F of x is just function notation. That's the same thing as y equals x squared. And this function, the parent function, looks like this. It starts at 0, 0. As you'll see, most of these start at 0, 0. And it goes up 1 and to the left 1, up 1 and to the right 1. It ends up making this nice parabolic U shape, right? It's not pointed at the bottom. It's not a V. It's a sloped off U shape, a rounded U shape. You'll see on most of these that they're going to start at 0, 0. The next point, they're going to have a point at 1, 1, most of them. And then a lot of them will also have a point somewhere else, right? Some key point somewhere else nearby. Here are some more parent functions. The cubic function, y equals x cubed, is the parent function, right? It starts at 0, 0. It goes to 1, 1, and it goes to negative 1, negative 1. And it makes, again, more of a parabolic sloped curve here, right? Where it goes through all three of those points, but not in a straight line. It doesn't just go straight through them in a line. It slopes off and goes through all three. It makes that nice vertical S shape. The inverse of the cube function is the cube root function. There's its parent function, cube root of x. It also goes through 0, 0, 1, 1, and negative 1, negative 1. But instead of being a vertical S shape, it's a horizontal S shape. Again, curved and not pointed. Another parent function, the square root function, f of x equals square root of x. That's the parent. Starts at 0, 0. Also goes through 1, 1. And instead of having, it doesn't have a left side of the graph at all. So if we talked about the domain of this one, it doesn't go past 0, right? It starts at 0. The domain of this one is from 0 to infinity. On most of these that we've looked at, we haven't really explicitly talked about it, but the domain here is negative infinity to infinity because it goes as far left or right as you want it to. The range is from negative infinity to infinity because it also goes as far up and down as you would ever want it to. For the quadratic function, the domain also goes far left and far right, so the domain is negative infinity to infinity. The range, however, is a little different. It won't go down as far as you want it to. The furthest down that it goes is to here, right? It'll go up as far as you want it to, though. So it stops at 0, actually touching that point at 0 and going to infinity for the range. For the cube function, this will maintain its rightward angle and leftward angle, so the domain and range here will both be negative infinity to infinity. The same exact thing on the cube function. It's going to match that domain and range. The square root function, you see the domain starts at 0 and goes to infinity. The range also starts at 0 and goes to infinity. It'll keep rising. And I think these are our last two parent functions here. The absolute value function, y equals absolute value of x. It starts at 0, 0, goes through 1, 1, negative 1, negative 1, and instead of a U shape, this one does make a pointed V shape. And the final is the reciprocal function. This we're going to see a lot of rational functions later on in the unit. This one has an odd domain and range. It does go through 1, 1 and negative 1, negative 1, the parent function does. But the domain here is a little bit strange because it goes all the way from negative infinity up to almost 0. And you notice that it never actually gets there, right? It follows that line. And then it starts at 0 again and goes to infinity. So our strange looking domain here is negative infinity to 0, and then 0 to infinity. And the range is also going to be that same exact thing because it goes all the way up, almost to 0, right? And slopes off. Then it goes from 0, not quite 0, and slopes back up. These are called asymptotes here. This is a good time to point this out. This 0 is an asymptote. It's a line that graph just never crosses, right? It never quite touches, it never quite crosses that line. There's a vertical one here as well that graph never quite gets to. It tries to get to it, gets closer and closer, but can never quite touch that dashed line. All right, as we try to apply translations, translations happen when you add or subtract to one of these parent functions. Notice that there's nothing multiplied, right? There's nothing crazy multiplied out here. We just have a number added or a number subtracted. What we need to do, the first step to all of these, is to look at what is the parent function. What's the main idea? What's the main thing that's happening here? And in our G, the main thing that's happening is that we have an absolute value. You see that? The absolute value bars? And so we know our parent function is going to be an absolute value. We can go back and look at what that looks like, right? These are handy to have memorized, these parent functions. You can go back and relate to these as you need to throughout the lesson. So that's what the parent function looks like, f of x equals absolute value of x. I just have that graphed right now, the f of x equals absolute value of x. If I want to graph absolute value of x minus 3, if you ever add or subtract, that's going to be a translation. That's going to shift your graph up, down, left, or right. And we can make some rules here where I'm just going to use an absolute value for an example. If you add or subtract outside of your parent function, that's going to shift up or down. And in fact, a positive is going to shift it up, and a negative is going to shift it down, okay? So since this is outside of that main little piece of the function, I'm talking about outside of this or inside of this. You can also add or subtract inside that. You could add or subtract within the cube, right? It could be like x minus 5 cubed. But if we're adding or subtracting outside, which is what's happening here, it's going to shift it up or down. Since this is a negative 3, that is going to shift it down 3. So I'm going to take all 3 of those points in my main function, and I'm just going to shift them down. 1, 2, 3. The same thing with that point 1, 1, shift it down 3. Negative 1, 1, I'm going to shift it down 3. I just shifted them all down 3 units. And now I can draw my V shape back through. Notice what happened is my entire graph was shifted down 3 units. You see that? The entire graph was shifted down 3 units. We can do the same thing with the next one. You go back and look for your parent function for f of x equals x cubed, right? Because that's the main thing that's happening there. And this is what a cubic function looks like. That's what the parent function looks like. We can go back and look at it if we need to, right there. See it? X cubed. This one, since we have a 2 added, and it's not inside, it's not within the main portion of the function. 2 is added outside, then we're going to shift it up by 2 units. Every single point will shift up 2 units, up 2 units, up 2 units, and then try and get the same basic shape here. Notice the whole graph, we just shifted up 2 units. This is a good thing to remember. Anytime we add or subtract outside, it shifts it up or down. All right, the opposite happens with the inside. If the outside shifts it up or down, the inside shifts it left or right. Shift left if it's a positive, or right if it's a negative. I'll put a plus sign here so that's not confusing. But if we have x plus a number, that's going to shift it left. If we have x minus a number, that's going to shift it right. This is counterintuitive here, right? It does the opposite of what you think it would. Inside, we're going to see that in a later part of this lesson as well, where if we multiply inside, it does the opposite of what you think. So on this one, we have what's our parent function we want to know. It's squared. Quadratic function, the parent function for a quadratic, for an x squared, looks like this. It goes through 0, 0, 1, 1, negative 1, negative 1. And what we have here is a plus 3 inside. If we go back and look at our note, a plus inside is going to shift it left. So we need to shift this entire thing left 3 units. 1, 2, 3. Every single point, I'm shifting left 3, left 3. And then I can draw the same exact basic shape. And notice that I just took this entire graph and shifted it left 3. I took every single one of those points and shifted them left 3. I should have been noting this as we go, but the colored graph that I'm doing is the one that we're trying to graph. The same thing here. The black ones are the parent functions. The colored ones, the blue ones here, are the actual functions that we were trying to graph initially. All right, if we combine translations, we've got square root of x minus 3 minus 2. We ask ourselves, what is the main thing, the main idea here? And that's that there's a square root. You see that? There's something happening inside the square root, and there's something happening outside the square root. But in general, our main idea is we have a square root. So that's our parent function for a square root. If we want to graph this, this plus 2 is going to shift it down 2, down 2. This minus 3 is going to shift it to the right 3. So I need to shift down 2 and right 1, 2, 3. Every single point, I need to go down 2, right 1, 2, 3. See that? And then I can get the same exact basic shape of my graph. Every single point got shifted down 2, right 3. I could take this point over here as well. Shift it down 2, right 3. It would end up back on that graph as well. Graphing a function with a vertical stretch. All right, if we multiply, the same exact things happen, where if I have, I'm going to use absolute value again because that's what's given to us, but if I have absolute value of a number times absolute value, a number x, right? Multiplying times. There's no plus, there's no minus. If I multiply on the outside, that's a vertical stretch. That really affects what I like to call the slope, right? It's not the slope, but we could treat it as if it were a slope. And a number multiplied inside is going to be a horizontal stretch. We can call that well, we can't really call that the slope. There's not really an analogy there. It's sort of the opposite, but this, I say stretch here, but it can be a stretch or a shrink as well, right? It can stretch it or it can shrink it. So if this number out here, that can also be a shrink. If this number out here is greater than 1, it's going to be a stretch. So like if that's a 5, a 2.3, a 1.5, that's going to be a stretch. If that number is between 0 and 1, then it's going to be a shrink. That would be something like 0.5, 0.3, 0. Whatever. Anything between 0 and 1 is going to be a shrink. And the exact opposite applies out here. The exact opposite applies when you have it inside. All right, so these functions that we have, every single time we have an absolute value, so we can have our parent function here, absolute value of x. For the first one, I'll try and color code. For the first one, I have g of x equals 2 absolute value x. That's multiplied on the outside. And so it's going to multiply every point. It's going to stretch it by 2. Essentially, I can act like it's a slope of 2. That's why I have this underlined. It's not a slope, but we can treat it as if it was a slope of 2. Start with our original point. 2 times 0. That's 0. All right, 2 times 1. That would be 2. 2 times 1. Again, the y value. 2 times 1 would be 2. And notice that it's sloped up more. It's more sloped. It's steeper. It was a vertical stretch. And that number out there, we call it the stretch factor. So we can say this is by a factor of 2. Vertical stretch by a factor of 2. For this, we could call it a vertical shrink by a factor of 1/2. Vertical shrink by a factor of 1/2. And here's where you're going to really see where I'm going to talk about the slope. So we're still starting with our initial spot. But to get to the next spot, I'm going to use this as if it were a slope. So instead of going up a half the distance and having to plot a half, I'm going to use that as a slope. So rise over 1, I'm going to go up 1 over 1, 2. Up 1 over 1, 2 in each direction. And notice that it shrunk that graph. That graph is now less steep. We have all three of our graphs on one xy axis here. I have them color-coded so that the black one is your parent function, the purple one is the vertical stretch, and the red one is the vertical shrink. All right, we said that if we multiply outside, it's a vertical stretch. If we multiply inside, it's a horizontal stretch or shrink. And so this is actually going to do the exact opposite. And so instead of being stretched outward, to left or right, since it's inside, it's going to stretch it horizontally. You see how I have that here? Multiplied inside, which stretches it horizontally. So it's going to stretch it horizontally. But instead of multiplying by 2, we're going to divide our horizontal distance by 2. So instead of this one going out all the way to 2 here, it's only going to go half of that distance. We're shrinking by a factor of 2. So instead of going out to 2, we're going to go out to 1. Instead of going all the way out to 2 here, we're only going to go out to 1. And the same thing on this on the left. Instead of going all the way out to -4 here, we're only going to go out to -2. We're just halving the distance each one of those goes. Then we can connect our dots the same way that the problem is, and you can see that our graph looks very similar. It's just shrunk by a factor of 2, right? We have one more transformation that can happen, and that's reflections, okay? And so if you have a negative multiplied on the outside of, again, the main idea, right? So if it's absolute value of x, if there's a negative on the outside, it's going to reflect it across the x-axis. The x-axis is here, right? And so it's basically going to take it and flip it this way. If it's multiplied by a negative inside, so something like absolute value of -x, right? It's going to reflect it across the y-axis. And so x, y, there's the y-axis. It's going to flip it this way. A negative on the inside is going to flip it left to right across the y-axis. A negative on the outside is going to flip it top to bottom across the x-axis. Let's see an example of that. So we have a graph given to us, and it says that we want to reflect it. We want to graph a y equals -f of x, which is going to reflect it across the x-axis because that's outside, right? Negative on the outside. Reflecting this across the x-axis, this won't go anywhere. This one, we're just going to take all of them and flip them this way. They want to be the same distance, but we're going to just flip them the opposite way. So this one, instead of being at 3, we're going to go all the way back to -3. Instead of being at 4, we're going to go all the way back to -4. Instead of being at 5, we're going to go all the way back to -5. And then we can connect the dots essentially the same way that we had. So that blue graph is our reflection across the x-axis. My connecting the dots was poor, I know, I'm sorry. I apologize for my lines being so crooked. Let's see another one of those. All right, we have a little bit of everything going on here, right? So the first thing we need to look for is what is the main idea? In the main idea, the parent function here is going to be x squared, which is a quadratic. We know a quadratic looks like this. Our quadratic is going to be a little bit different because it's going to be shifted to the right by 2, up by 3, shrunk by a factor of 1/2, and flipped across the x-axis. So let's try and do this in parts here. The first thing we can look at is moving it over, okay? We can shift it. We know our original point is going to be shifted to the right 2 and up 3, right? 1, 2, up 1, 2, 3. That's going to be our new starting point there. So essentially I took this point, shifted it right 2 and up 3. All right, now we can still, without having to think too much about the reflection and all that jazz, we can still just look at that whole thing as if it were a slope. And then in the end, we can check and see, was it reflected? Was it shrunk as we think it was? So if we look at that entire thing as a slope, -1/2, I need to go, to get to my next point, I need to go down 1/2 in each direction. Down 1/2, down 1/2. And then my graph ends up looking like this. That's n of x, not f of x. So let's write that as n of x equals -1/2 x minus 2 squared plus 3. All right, let's go back and just analyze this and check it real quick. Was it shifted? Does our graph shift right 2? Yes. Does it shift up 3? Yes, it does. Does it reflect? Yes, it does. It's flipped over upside down. And does it sort of compress itself? Does it unstretch itself? Yes, it does look flattened out. It does look compressed. All right, last one of this type. What's our main idea here is what we want to know. The main idea is that we have a square root. So we're going to start with a graph of y equals square root of x. I like to start with the shift first. And so my first point is going to be shifted to the left by 2. Left 1, 2. And then we're reflecting both over the x and over the y. Reflect over the x and reflect over the y. So instead of going up and right, if we reflected over the x, it would go down, right? We would flip it this way. If we reflected over the y, it would flip it this way. So we need to essentially do both. Instead of, we're going to go in the exact opposite direction. So instead of going up and right, we're going to go down and left. I totally missed that point. Down and left. That's what our new graph is going to look like. V of x equals negative square root negative x plus 2.